provided for homework. Can somebody read that problem out for us, please? Alright.
If the radius of motion, on the circular motion is double, what happens to the force?
If the radius is doubled of an object in circular motion, what happens to the force? Okay? So, from yesterday, or from yesterday, what can you tell me about the force of centripetal motion? What's the force formula?
Something F something something.
F
Over R.
Okay. Yes, that is our formula. Very good. Now, here's what I want you guys to think about. The location of R. Put it away until lunch. Put it in your pocket. Whatever you need to do. As long as it's away. So mv squared over r is our formula. Now, the problem said the radius doubled. So if you normally had, let's say the radius for the first problem, so let's make up a scenario. Scenario 1, let's say the radius was 5. Okay? Let's say the radius is 5. And then in the second problem, it said that the radius doubled. So in scenario 2, the radius would be 10 here. What's going to happen to your force?
Quadruple.
It's going to be what? Half. Why half, Christian?
Because the radius doubled, therefore.
Yeah, Christian.
It's like times 2. So.
It's like times 2 in the what?
Denominator.
Denominator. Guys, why are we still talking? Come on. This way. Again, the radius was 5, and then it became 10. So we doubled the denominator. When you double a denominator, it's like multiplying by 1/2. Again, and this is the question I know Star asks a lot for area of triangle. 1/2 base times height, or base times height over 2, right? Same thing. So if you suddenly put a 2 in the denominator here, because we doubled the radius, right? You put a 2 there. That means that it's really like you're putting a 1/2 out in front. Again, if I wrote it this way, F equals mvt squared all over 2r, or if I wrote it this way, mvt squared with a 1/2 in the front all over r, these are the same things. Again, if I double the radius, and again, these are absolute value, I know that. If you double the radius, it's putting a 2r on the bottom instead of an r.
Lower.
Well, it's the same thing as putting a 1/2, right? So what you can tell always is this. If you double the radius, you're taking 1/2 of the original force. Again, if you double the radius, it's half of the force. This is so important because when you drive, this is how driving works, guys. And nobody knows this one. This is a random driving tip that most people don't know. When you are going around a turn, there are certain ways you should change lanes and certain ways you shouldn't. Ones that are more safe and others that are not. So let's go through an example of that implies this radius thing right here. So let's say we have a person driving around a turn.
I just don't turn the wheel as much.
Double the radius is half the force. So here's your car. There's one lane out there.
Doesn't matter what size the car is.
Okay.
Nah,
So you are currently in the middle lane.
not really. It just depends.
Yeah, come on, man.
It only
You're currently in the middle
depends on
lane.
the size of how fast
Okay?
you're going.
There's 3 lanes in the highway now. You're in the middle lane and you're turning. And the question becomes this. You need to change lanes because there's traffic in front of you. You can either move in or you can move out. The question becomes which one should you do and why?
Move out.
Okay? You said move out.
Yeah.
Justification?
Because it's easier to move out. Because if you want to go in, you're going to have to push more force to go inside.
Absolutely right. And we're going to prove that in a minute. He's absolutely right. Think about it. If you're turning, because he's using logic to answer, and we're going to prove
you have to
mathematically
do
why his
this.
answer is correct.
At that one, you just
As you're
let it
turning
go.
in, think about it. If you're turning in, to move out a lane, you just have to lightly let you move your wheel over, right? It kind of moves on its own. But to move in a lane when you're turning, you're going to really jerk the wheel to the left to get this to actually move in. So the higher, you need more force to move it in. How come? It all goes back to centripetal motion. Because here, by moving in, you're making the radius smaller. By moving out, you're making the radius bigger. And a minute ago, we said that if you make the radius bigger, if you double the radius, the force is actually only half. So by moving out, you're doubling the radius. So it's less force on you. By moving in, you're like halving the radius. So let's do an example of this. Okay, same car, and and we're going to do 3 scenarios. Scenario 1, the mass of the car will always be 1,000. Let's start with that. No matter what, the mass is 1,000. We'll say that the velocity is 10 meters per second, just to be simple with this problem, okay? Just for simplicity. We'll say that in this middle lane, your radius is 5. In the outer lane, your radius is 7. And in the inner lane, your radius would be 3. Again, assuming that this is the center of the circle, where you have radius 1, radius 2, and radius 3. Okay, again, if you're on the outer lane, you're thinking about like going through a circle or an arc with a radius of 5. The minute you move in, your radius has become smaller. Now your radius is only 3. Again, that's 3, that's 5, and that's a radius of 7. So as you move out lanes, you're really increasing your radius. And we saw a minute ago when we doubled the radius, it lowered the force. So now we're going to talk about this and actually solve. So in the first case, when r equals 3, again, when r equals 3, we're going to have 3 cases. R equals 3, r equals 5, and r equals 7. And we want to figure out what the centripetal force is in all of these cases. It's the same formula no matter what. mvt squared over r. Again, I can start dropping the absolute value. Can anybody explain why I can start dropping it? Because it's squared anyway. So even if this number happened to be negative for some reason, and it was a negative speed, we said take the absolute value, right? You're going to square it anyway. So you do need the absolute value theoretically, but realistically you don't really need it because you're squaring.
If the velocity was negative, does that just mean that it's going like counterclockwise?
Yeah, it just means that you're going in the negative direction. That's all it would mean there. Okay, but again, you're squaring it, so your force is still going to be positive. Yeah, remember, guys, your acceleration is toward the center of the circle, and your force and acceleration are always in the same direction. So your force is always going to be directed toward the center of the circle. And let's explain how that works here. So, with this one, we have, again, we're using this formula.
So basically, we have the same numerator.
The numerator will not change. 1,000 is m times v squared all over r.
You're confusing me.
I gave you the mass and velocity, so the numerators are all going to be the same here. The mass was 1,000, velocity was 10. Now, God bless you. What you notice here again is that the denominator is smaller here.
Shh,
The smaller the denominator, the bigger the answer. Again, the smaller the denominator, the bigger the answer, because you're dividing by a smaller number. Okay? It should be, but I'm just going through each one. Just going through each one, Julian. Something is a common logic to one person, not to others. So here, we're dividing by 5. Okay, so this number is going to be, this will be 100 times 1,000 will be 1, 2, 3, 4, 5, 100,000. Okay, so this is 100,000. The numerator is always 100,000 for each of these.
20,000, 20 something.
That's just 20,000.
I'm talking about the 7. Oh no, like 15 something.
This one is 20,000, the force.
The first one is
13.
This is 33,000.333. 333.3333. And here, what do you get?
14.
Why didn't it work in the second one? When I put second return, and I tried to do it, like just cancel them, give me wrong answers. You know, when you go back to the...
Yeah, you have a second entry to re-enter and you change the 3 to a 5 or the 5 to a 7. You should get these numbers. Check again.
Why didn't you round?
Now, I'm rounding, guys, I'm rounding. Here's what I want you to notice.
She's like,
From your notes yesterday, we said when a NASCAR driver is going in a circle, what keeps the car in motion? Friction. So the centripetal force that is acting right now is really friction, because that's what's going on here. We're a car driver driving around a bank turn. Okay, so it's friction that's helping us. So, looking at this problem, the higher force means that your car has to have more friction force. More friction force. So this means that as you move in the turn, so as we said before, as Byron said, as you move in radius, you notice that the force needed to do that is much higher. the friction force on the tires is much higher than it is here. And that's even higher, just pick it back up, and that's even higher than it is here. Again, the highest friction force is the smallest radius. You don't want to have a high friction force because that means that your car could possibly slip. Your car could possibly slip. If there's too much friction force and your car can't withstand that friction, the car could veer off the road. So whenever you're going around a turn, you want to move to the outer lanes. That's the key here. That's our conclusion. Again, moving to the inner lane makes it more of a force. Staying here is our baseline. Moving to an outer lane means that what here? Means that the force is going to go down. Okay? The force is going to go down. Hold on to your notes there, please. Again, the force is going to go down for this one. So here is the baseline. If you move in, it's a higher force. If you move out lanes, it's a lesser force. So if you're taking a turn here, in this direction, now you'll want to move out lanes like that. As in before though, before our turn we started here in the middle, and we had to move out lanes like that. Again, when you move out when you're driving, and I'm telling you guys, I do this all the time, whether you realize it or not, you do it too. If you're going on like an exit ramp or an entrance ramp, and you have to change lanes, which you usually don't want to, you move out. It makes it a lot easier. No matter which way, even if you're turning this way, you're turning this way, to move out lanes is a lot easier than to move in lanes.
Why would you want to move that?
If there was for some reason there was like an accident here, and you had to avoid it, which way would you move? You move out. You don't move in. And you're gonna use your instincts, obviously, right? If there's an accident or something, okay?
Isn't it possible that you could flip?
If you move in, there's several things that can happen. The friction force can be too little, so you could flip. You could slide off the road. Even moving out, you could flip or slide off the road still. But there's more of a chance if you move in than there is moving out. Okay? Because you need more force. Because you need more force. I saw a hand in the general. No. What do you mean the sense of drifting? Like how do cars drift, you're asking me?
No, I'm not asking. Would it differentiate from like what's going right now, like the same kind of logic?
I don't know too much about drifting, to be honest with you.
What kind of engineering?
The general idea is that what you're doing is your car is sliding translational.
Right.
So it's sliding against the rotation of the tire. That's why they call
I think
it
it's momentum.
sliding over.
It's the
Sure, it can affect this problem. You could fishtail a little bit if you go one direction instead of the other, but
Is it more like the opposite way?
yeah.
Cars that are not judging it.
No.
Whereas when it's kind of effect, which is like,
you can think of this as an example of that. I don't know how to answer that with the right answer. I'm not going to tell you one thing because I don't know.
The way it should be, like.
Now, what I do want to mention is this. No problem. In the scenario we just had, we had a cup of water on some sort of a surface. It was in a basket. I can draw three-dimensional baskets only.
Are you serious?
Okay, that was the basket we just had, and there was a cup of water sitting in the middle, and it was spinning in circular motion.
Centripetal force goes up to the basket too.
Is it what?
Does it hold on to the basket too?
It does apply to the basket also, yes.
So it's like, so the water blows the cup into the basket.
That's exactly what I'm going to ask right now. I'm going to talk about forces and how that works. Do whatever you need to do.
Why do you always do that, huh? Why do you always have to get ahead? I
For
hate
this example.
for history for bonus points.
For this example here, guys, when you're spinning this around, you need to think about every different instant in time. For example, here, when it's at the bottom here, you have gravity still acting downward. Okay, if gravity acting downward, what pushes back up? The normal force. The normal force. Now, what keeps the basket in motion? Be careful. The rope, which is what force? Force of tension. So there's a lot going on here for this problem. It's very complex, even though it sounds simple. You have the rope providing a tension force. Okay, I'm not going to write this stuff, so whatever you need to write, you write. Okay, the rope provides a tension force on the basket, which holds the basket in motion. The basket pushes up on the cup with a normal force. So again, the tension in the rope holds the basket.
Okay, makes
And then
sense.
the basket holds the cup with a normal force. Because the cup wants to move down due to gravity. But the basket is holding it up. When the cup is up here, or when this whole situation is inverted, okay, when the water's like that, and this is now
The basket is
inverted
still
in this
pushing up
direction,
on it, though.
the cup now, when it's spinning this way, the cup is pushing up now. Gravity's pulling down, and the normal force is pulling down now. So here, again, here you have gravity,
So what is
so we
the
can call
water
this the
called?
weight. You have the normal force acting up. Up top, you've got gravity acting down.
Wait, why?
Okay. We're talking about this where it's spun in 360 degrees. We're spinning this now again. So when it's up top, you have the weight pulling the water down. So it wants to fall, right? It wants to fall. And it's spinning like this. So it's got an acceleration acting, okay? So here we want to think about the fact that the weight is acting down, so there really isn't a normal force. There might be, but we don't know what the value is. Here, the normal force really does exist. But when this thing gets to the top, it's kind of like it's floating up there. It's kind of like it's floating. And it's moving so fast that it's not floating long enough for the water to fall out. But really, if you pause, what's happening is the water wants to fall down. And if you could freeze it up top somehow, you could invent a device that would literally freeze the rope at the top, what would happen with the water? It would all fall down. It's not falling down because you're going so fast. Okay, it doesn't give it an opportunity to lose its inertia and just fall down, or to use its inertia and fall down.
Okay, gotcha.
If I went like this and like stopped at the top slowly, the water would come down. You know, it won't work. Yeah. I'm doing it at constant velocity. Notice I was doing it at constant velocity when I spun it. I wasn't going like really fast on one spot or the other. I was going slowly.
What if you increase it gradually?
As long as it's a constant velocity, though. So if you're increasing your velocity at a very slow acceleration, that's fine. But if you're increasing it at a very high acceleration, then it's not going to work. That's the difference between acceleration and jerk, the third derivative. Hey, Siri. What if the guys? I can't hear him. Come on. It's like 3 times a day. No. I don't need you to repeat it. I need you all to be quiet so I can hear him. Thank you. I appreciate it, but I want everyone to be quiet. Hey, Siri.
It's like you were spinning it in a basket, and all of a sudden, like the cup just like rips in half. Like will the water just split and it's hanging like.
Yeah, because the cup is holding the water. So you can go even further and say that the cup is providing a normal force on the water then, sure. But if the cup goes away, the water is just going to shoot off tangentially. Remember yesterday when we did the one with the key, and when I let go here, it shot tangentially? So if this cup exploded right here, and this was going in this direction, the water would all shoot in that direction. Tangent to the circle. Again, the circle looks like this, right? And we're going in this direction. So if the cup exploded here, it would go off that way. If the cup exploded over here, all the water would shoot straight down. If I was doing this, and the cup exploded at the bottom, the water would all shoot off that way. And it's kind of logical. Imagine if you had a device that could explode or could release the fluid, whatever it may be, at a certain point in time. If you release the fluid at the bottom, it's going to just naturally shoot that way, right? All the fluid will go off that way. At the top, if I'm rotating and it gets to the top, where does it want to go? It wants to go this way, right? Isn't that the direction of the motion? This way, and it's tangent. Eventually it will, but it will go off this way. It'll go off tangent, and then it'll fall down to gravity.
It'll be like
But the general motion is always tangent.
It'll be like a projectile.
It will be like a horizontally fired projectile. Now, if you study AP calculus or AP physics, what you notice here for an AP physics problem would be you would have circular motion. You would have circular motion where the object is released up here, which then means it shoots off this way, and now it's a horizontal projectile motion problem. Again, remember the problem where we said a bullet or arrow is fired from a cliff, it goes a certain distance, find the height of the cliff, or find the distance it traveled based on the height of the cliff. That's what this problem is. If you let go of this object at the top, it's going to fire off horizontally, and eventually it'll come down like this. That's projectile motion. It's horizontal projectile motion. It will eventually come down, yes, over a longer period of time.
I don't see how if it's at the top, it's going like, it's freeze at the top.
We didn't say freeze it. Freeze it, it'll come straight down. I said if you let go of it, or if the cup explodes and it's still moving. If you could physically freeze something, the water would just drop straight down. Absolutely. But if you actually were to let go at the top, or the cup exploded at the top, the water would want to go in the motion it was going. Since it was going this way, the water would just all go this way and come down like that. Okay? Again, it's not freezing. Freezing was the other one. So again, the idea here is this. The radius has a huge impact on this problem. And the centripetal force is never going to be the same. Sometimes it's the normal force, as we saw here. This was the centripetal force. It was the normal force. The centripetal force here, believe it or not, is the weight. It's the only force that's acting on it. If you had a car, it was friction. With the electron, it was the electromagnetic force that kept it in motion. So the centripetal force can take on many roles.
I know, like, it's not always.
I hate centripetal force already.
Isn't that normal force and the weight the same?
Are they the same? Usually, for an object at rest on a table, the weight and normal force counteract. But remember when we said, like, remember the example of the elevator? And if you like jump on the elevator, you kind of float. Or if you jump, or if you're accelerating down, you bring a scale on the elevator, it won't show up. That's kind of like this. When an object is in some sort of motion, the normal force and the weight don't always balance. That's why at the top there is none.
It pushes it back down a little bit.
I understand, but I'm saying, like, if you were to jump and the elevator is moving down, you might hang time for a little more because it's moving down. So for you to get back down, it'll take longer because it's moved a little bit by the time you jump. Okay. Everybody ever think of you guys seen like Looney Tunes, right?
Yeah.
You know when like the coyote always hurts himself trying to kill the roadrunner? One of the simple examples is when you see like you'll see like him there. Like if you were in an elevator, the elevator would start to fall and his head would just hit the elevator, right? And you know that wouldn't really happen because if the elevator is moving, your body's going to move with the elevator because you're moving together in tandem. But if theoretically the elevator just dropped and you were standing still and you froze in midair, your head would hit the top. It's never going to happen though, but the idea of jumping is the simulation.
Unless the elevator was really small.
Yes, unless the elevator was very small and it accelerated very fast, and you didn't have time to catch up to it.
I don't know if it's working, but like I
Okay.
You told me, yeah, you said you brought it in. You brought the scaling.
Yeah, I was like in the air.
It does work. Try it sometime.
Well, you
guys.
tried it?
Try it like you're at an apartment complex, a building at work, anything. Don't do it with other people in the elevator.
Yeah, get fired. Yeah.
Not with other people in the elevator.
And the elevator's going down, just jump up as is and straight down and you'll be.
I'm sure if somebody gave you a hard time, you could say, I'm trying a physics experiment actually, and they wouldn't have a problem with that.
Yeah, whatever.
Hey, no,
Oh,
I'm
yeah,
not there
yeah,
with
yeah,
it. He's doing it.
So why do you need to scale to jump up?
Astra would be like,
No, I just what are you doing?
What would they be like?
they'd be like, what the hell are you doing?
What happens?
I think they'll even cut that.
That's almost like a freshman with
Yeah, because not only that, but
I know, right?
Hey, when you have somebody that you gotta train,
I'll
yeah.
make them do everything. And it's like about when you're with people, it's like you're hanging out. So it's like time goes like that when you're hanging out with people. And then I work in the kitchen too, so it's like everybody's always talking to the person around.
Let's take a look at number 4, please. Let's take a look at number 4.
I was going
Wait, where are you looking?
On the board here, number 4.
The race car is moving along the. Nice.
Let's do number 4 here, people. Number 4.
I have a question. For velocity? No, it's acceleration. If the car has a tangential speed of. What?
So we got a race car moving along a circular track with a centripetal acceleration. Okay, centripetal acceleration of 15.4 meters per second squared.
Did I write this?
If the car has a tangential speed of 30 meters per second, VT, what is the distance between the car and the center of the track? Okay, so what are they asking you for here? The radius, again.
So
the
solve for
radius.
radius first?
That's the only hard parts of these problems is actually determining what to do. Okay? When it says, what is the distance between the car and the center of the track, here's what you have to think about. There's the track, there's the car going around the track in that direction. Okay, the center point of the track is right in the middle. They're asking for this radius. Call it R. Okay, they say, what is the distance between the car and the center of the track? That's the radius. So pretty much it says, find R.
But it doesn't give you the force.
Okay.
Well, it gives you acceleration.
We know acceleration, centripetal, is 15.4 meters per second squared. We also know that the tangential velocity, VT, is 30 meters per second. And notice it said velocity, so I am writing VT here. Okay? And it doesn't matter what the absolute value now for this one.
What does it call speed?
Hold on one second. Does it matter what absolute value here if I take it or not? Because it's still 30 either way, right? Okay? Constant speed, where are you looking at?
Tangential speed.
Oh, tangential speed, sorry. Tangential speed, yeah. Sorry, so if you want to call it S, thank you. Why did I say velocity? Somebody said velocity, right?
I think, yeah, you said it.
Okay. So again, these are our two values here. These are our two values. Find the R value. Let's go to our notebook page so I can write a little more.
Do we have any mass?
Do we need a mass, guys? What formula did you have from yesterday?
Oh, F equals M. No,
Use the AC one. Very good.
I don't want to use the AC one. I don't know.
What page number was that?
Hold up.
In the book, it was page 236.
S.
This is page 236, number 4.
ST squared over R equals V.
I got it.
So, the acceleration was given again as 15.4. We're solving for the radius. The velocity was given as 30 meters per second. Please switch the A and the R. Okay?
Yeah, just to show you know.
Velocity, sorry. Move the A and the R, please. Move the A and the R. Solve analytically. So switch these two spots. Write it as R.
30.
I'm sorry you hear your fading. Let's keep that to yourself. So the radius is what we're looking for here. We have the velocity was 30. We have the acceleration was 15.4. Solve for the radius.
It's so difficult.
What is that, 900 up there? Is it 900 up
It's
there?
always the way, that way.
Change it. 900 over 15.4.
58.4.
I'm a B plus.
Okay, calculator.
What are the
people.
units of a radius, people?
Where?
Meters.
You, I'm trying to test them.
No,
Again,
The
why are units meters? Because it's a distance 1, or take a look here. When you square meters per second, you get meters squared
over
per second squared over meters per second squared.
You didn't put the squared on 50.
Very good. Cancel, cancel. That cancels with this. You're left with meters. Okay, you look at your dimensional analysis every
How
time.
about you put second on the 15.4 meters per second? I thought it was 15 meters per second.
Thank you.
It's like,
Well, he's right. He's absolutely right. That should be squared.
like, I don't do
I just listened to what I heard. Do it.
That's like
Absolutely.
Okay.
Now let's make one more statement before we go on to the next problem. Yesterday,
I know they get tired.
Palm?
so
It's a Windows phone.
yesterday we were talking about how centripetal acceleration means center seeking. So before
It
we
seeks
go
the
any
center.
further, we should know that the centripetal force also is center seeking because it's centripetal force.
Oh.
Well, how can we show that? The simplest way to show it is this. Here's your object. Okay, remember vectors? Here's our
Look on
object.
YouTube.
Our acceleration vector is directed toward the center. Again, the acceleration always acts toward the center, no matter where we are. We showed this yesterday with those triangles. Now, acceleration and force are always in the same direction. Where does that come from? Which law?
Newton?
Newton's, very good. Newton's law. So again, this is our formula from Newton's law. If the acceleration acts to the middle, the force also acts toward the middle. Okay, so I know we didn't write that yesterday, but I want to make sure we understand. Centripetal acceleration, centripetal force, they're both centripetal. They both act toward the middle. Now, depending on where you are, it'll be in a different direction. So if you were down here, then both your acceleration and your force act in that direction. Again, the acceleration, comma, and the force, they both act toward the center. So your acceleration and your force always act in the same direction due to Newton's law, F equals ma. Okay? Just keep that in mind. So not only is the acceleration center seeking, but the force is also center seeking. Okay? AC, comma, FC. They're both acting toward that direction. Let's take a look at another example. Let's go to page 238 and look at number 2. Okay, this is page 238, number 2. Now, for this problem, can I get a reader for number 2, please? Number 2, join.
But a bicycle is riding a tangential speed. Wait a minute. A bicycle is riding at a tangential speed of 13.2. Alright.
Meters per second.
2 meters per second around a circular track. The magnitude of the centripetal force is 377 newtons, and the combined mass of the bicycle and rider is 86.5 kilograms. What is the track's radius?
Okay. Before we start this problem, what's providing the centripetal force here? A bike rider?
377 newtons.
What's providing it though? What kind of force is it? What is it? How come? It's a bike rider on a track or a road. So there's friction between the tire and the rider. So again, the rider's going to be riding in a circle, probably tilting a little bit, right, when they're riding circles like that. But you're going to have some friction between the rubber of the tire and the road. So keep that in mind. I know it doesn't ask that, but always know what it's providing.
What page number is it?
This is page 238, example number 2.
what is that?
Page, get
You know those bikes, the real skinny bikes with the real
Yes.
those had like
Less friction, much less friction because less surface area, but they move faster actually.
I have a
that's
question.
scary.
Less air resistance on the tire as well. Less surface area reduces the air resistance. It's proportional to the actual area there.
I ever seen a race car and you ever seen the tires? Why don't they have grips?
Like, don't they have
Yeah,
grips?
they're just like.
I don't know too much about tire mechanics. That's a whole topic.
Cause I was thinking, I'm like, how are you gonna go faster?
I'm sure there's a reason that they have
Well, my
it that
dad
way.
told me why, but he just didn't know how to explain it.
Well, if you explain it to me, if you get it from him, tell me, and then I can try and interpret it. I can look it up too. We can just Google it. All right.
Mr. Howard,
Google.
I have a question. Since we're talking about bikes, do you think a motorcycle is faster than a car?
Depends. Can it go faster than a car?
Yeah.
Theoretically, sure, but the motor's smaller, less mass. So it's like which one outweighs it, right? More power in a car, but more mass to pull. So it depends on which way you're looking at. If you're talking about getting to a max speed completely, like which one can top out the most, I would probably say it'd probably be a bicycle, a motorcycle, not a bicycle, but a motorcycle.
Because bicycles are like
Because they're less weight.
cylinders, or
You know,
but
there's
they're
less
less weight.
mass,
Yeah.
but they don't have as much power. They're like V2s or V6s or V4s. They're not like V12s like Camaros. If you're running a car like that, then maybe not. It's theoretical.
So you just know that it's friction because it's moving on the surface.
Well, because I know what's stopping the bike guy from sliding out from his
I have one in
path?
my
Friction. What's keeping it in
I
motion?
drive,
Friction.
but when I'm on
Okay? So here's my velocity. Here's my force. Here's my mass. Solve for the radius. It's the same problem again, guys. So we have not tangential, centripetal force.
when I'm on my bike, Mexico, come on.
How? You should have verified that.
Talk about that.
I see what you're asking.
Talk about it.
Yeah, I was gonna, I thought you got it.
Well, we're trying to get the
Yeah.
radius? Oh, yeah.
Again, guys, it says, what is the track's radius? So in this problem, it's no different than the last one, except now FC and R are switching spots. Earlier, we switched AC and R. Those two flip-flop. But now we're switching these two. So plug in the values you know. You know the radius is equal to the mass
Where's velocity?
times the velocity squared
13.2.
all over the force.
You just switched.
Okay? Again, what did I do? I simply switched R and FC. You're solving for R. If you switch those two, you get this equation in the middle.
77.
Do they count the
39.97. 39.97. Somebody else check for
Read
me.
it.
Somebody else check for me. Hey, somebody else check for me.
They give you what A. There's two formulas.
Again, you have two formulas, guys. A equals B squared over R, or F equals MB squared over R. Depending on the scenario you're in, you have to know which one to use. Okay? Again, depending on the scenario, know which one you need to use.
All we gotta do is know if we're looking for, force and acceleration, right?
Correct. Absolutely. If you're given a force, then there's a good chance you're going to use the force.
But if we're given a mass, if we're given a mass, can we assume
Yeah,
we're
but the mass of the bicycle is
We're not necessarily.
Yeah, I guess you could. Yeah. Because the mass won't help you find the acceleration, it'll only help you find the force. Good way of thinking about it. Let's do number, what do you want to do? 4? All right, let's do number 4. Again, guys, your answer's down here. Your answer's right here, guys. Check your number, please.
905 car travels around a circular track with a circumference of 3.25.
We did number 2, right?
There's magnitude.
We did number 2, now we're going to do number 4.
What is the car's tangential speed? That newtons.
Notice the kilometers here, be careful.
Oh, we have to convert.
So you have to convert.
No.
Okay, so I boxed and circled the stuff that's good, and I underlined what we need to figure out. So we've got a mass. When you have a mass right away, as Houston said, you're probably going to use the force. You have the mass, you got a force here, you got a circumference.
Do we need it?
Circumference. What can we get from the circumference?
The radius.
The radius, and then use the radius to find the tangential velocity.
Is it 2 pi r or pi r
Okay.
squared?
6.28. 2 pi r.
2 pi r, yeah.
So let's do this problem. I'm going to erase the last one now. So here, we got a few steps to go through.
3.25 divided by 2 equals 1.
First, that's our force.
1.625 pi.
Here's our mass.
905 kilograms.
We have a circumference equal to
3.25 kilometers.
3250 meters. Again, guys, it's in kilometers. Please convert. Please convert right away. Now, you can't use, again, you can't use the circumference in this problem. So you have to figure out what the radius is based on the circumference. Here's a simple way to do it, and I'm going to show you guys a way. You don't have to do this. If you want to find the radius as a number, that's fine. I'm going to show you analytically. And if you're in calculus, it's like the constraints with optimization we're going to do right now. You solve for one variable, plug it in the other. Okay? So here, guys, you don't have to talk every time I talk. Come on. Here, what we're doing is this. Start with the formula for circumference. C equals 2 pi r. Everybody see that? C equals 2 pi r?
Yeah.
Solve for the radius. How do you get rid of the 2 pi?
Divide by 2.
So the radius is just the circumference over 2 pi. Is that agreed?
Yeah.
Isn't that what the radius is?
Yeah.
So when you do your formula now, and you say F equals mv squared over r, you can simply take that quantity, c over 2 pi, as a variable. You don't have to put it in the numbers, and you could replace the r with it. Again, you have a fraction over a fraction. No big deal. So you can write this as fc equals mv squared over c over 2 pi.
Doesn't the 2 pi go up?
Okay, and the 2 pi, when it's in the denominator, moves up to the numerator. You don't have to do this. Again, I'm telling you. If you want to find the radius, just take in the 3250, plug it in there, divide by 2 pi, you'll get the radius, and you can plug in the radius right there. That's fine. But I'm trying to show you ways to solve analytically. Okay, that's what I'm trying to show you here. Start. The problem is asking us to find the velocity, so solve for v if you're here already.
Because I was thinking how you know how you get the numbers.
There's no need to here, though. Just move it up to the numerator. So this equation here, people, this equation, I'm going to continue on the next page. fc equals mv squared over c over 2 pi.
mv squared over 2.
Transfer the program.
Over c 2 pi.
That's where we just left off a minute ago. Okay, that's where we left off. If you want to solve for the radius and get the number, that's fine. But now this becomes fc equals 2 pi mv squared over c. Again, it looks like this is crazy, but you know what? This is just r here. And instead of r, I'm putting c over 2 pi, which is what r is solved as. Once I know that, the 2 pi is in a denominator. Denominator of a denominator bumps up to the numerator. It's always the way it works. So it goes up there. So now, you've solved for the force of centripetal in terms of the circumference, not the radius. And we have the circumference. It's 3250. So at this point now, we want to find v, right? Wasn't that the goal of this process?
Yeah.
Find v. How do you move the c? How do you get rid of it? Multiply it. Good. How do I get rid of the 2 pi m?
Divide it.
Good, because I'm going to be left with 2 pi mv squared here. Divide by 2 pi m, cfc over 2 pi m equals v squared. And do what?
Square root.
Very good. Get rid of the square, put the square root. So if you want to get your answer for this problem and you don't want to worry about getting the radius ever, and you want to use only the circumference and the force and the mass.
If we don't have a
Just plug in those values.
Question. If we don't have a calculator, can we just leave it like that on
Yeah.
the test? We don't
Plug
have
in your
a-
numbers and show me where the numbers would go. So write the number in and then leave it on the graph. So literally just replace the variables with numbers at that point.
Alright.
Which gives you, in case you're wondering, 3250. What was the centripetal force?
140.
And the mass was?
86.5. 86.5.
905.
Oh, damn, that was the last one.
Last problem. I thought the same thing. Don't worry. And it was, I think,
Yeah.
Again, it does not matter which way you solve this problem. Please, if you want to solve for the radius and then use mv squared over r, that's fine. Okay, I'm showing you ways to solve analytically, so you can always plug in the circumference. You don't want to memorize this formula because you can always show where it comes from. You can always show where it comes from, so don't memorize these.
Karen,
Julian,
who said that?
34.9? You could be wrong, you never know. Can I get some other people to check?
I did it different. All I did was I divided the circumference by 6.28.
2.8. And you got the radius, and then use the radius.
Yeah, then I multiplied the radius
Times FC.
Yeah, then I divided
M.
0 by 905. And I got the answer my radical.
That's exactly right. That's the exact steps you want to do. Do you get the same answer, people?
Yes.
JC, you checked it? You got the same? Under the radical here, you got the same answer? What about units of velocity?
I don't know if I did.
Put a big parentheses here if you're correct, if you're confused, and put a big parentheses here. It might help your problem. Okay, it might help your problem here.
I had to turn around.
Open. Times. Close that one. Open. Ooh, 905. You put 9.5. That's the only difference. See that? See 9.5? 905.
Someone needs new glasses.
No, the decimal and the zero are next to each other, so I'm sure you just slipped. You get the same answer? Now, the cool part here is this, that Julian verified for us, if you find the radius and solve, you get this answer. And if you solve analytically, you get the same answer. Okay, so it does not matter. It's up to you to choose whichever way you would like to. Let's see one more problem.
Okay,
No,
you say-
let's start with the homework. I'll hand out your homework.
Don't think about it until you get it.
You have 2 nights, people. Front and back, 2 nights. Front and back, please.
Actually, no, I have one night. Wait, that's class?
All circular motion the last 2 days, guys. You can answer all these questions on here.
I'm not gonna, you probably use it. Oh, here.
We need one more.
And I want you to think about it. I don't want you to ask me questions right away, people.
Let's do it.
Oh my God.
We need
Is
one
it
more.
just
too.
Bridget absent? Is it only Bridget absent?
We need one more also.
I got
Is that it?
Oh, I didn't
Here, this year you can get mine. Sure.
Where's James?
Oh, I
Give your extra to this here. You got it already, didn't you? Because this is Bridget's. I knew there was one on.
And James got
If you instead of dividing by the fraction, you multiply by over C. I just moved that. But you're multiplying by the C. It's like you're 1/2 and 2 things. Same exact.